right, let's go ahead and go over quiz 2. Quiz 2 was focusing on unit conversions and chapter 3 content, temperature, heat capacity, that kind of stuff. All right, so here we have a question. Consider a saltwater solution, and we're given the mass and the volume, and then you're being asked what is the density in grams per milliliter. All right, so the trick here is recognizing the units here aren't quite right. So I'm going to take that into account when I set this up. So we know that density is equal to mass over volume, and my mass term here is 1.345 kilogram. So 1.345, and instead of the kilo, I'm just going to go ahead and put times 10 to the 3, and then grams. So once again here, instead of K, I just went ahead and put 10 to the 3, because sometimes it works out where they cancel out. All right, I can do something similar on the bottom. I want this to be a milliliter. So if I went ahead and put, let's just go ahead and put the number as written. So it's 1200.0, and I want to go ahead and say milliliters. How many milliliters would I have there? So you essentially just need to move the decimal place over a few spots. And notice here, so once again I'm putting times 10 to the 3 ml in place of the liter. So in this example, these cancel. And I think this is going to be an unusually small density, but I was just pulling numbers out of my head here when I was writing this problem. So as long as you set it up right and punch it in correctly, I get full credit. I wanted to point out once again that saltwater solutions are typically in the order of about 1. They're a little bit higher than water. You guys remember that the density of water, pure water, is defined to be exactly 1 gram per ml. So I just want to mention this here. If you come across this, the density of H2O is defined to be exactly 1 gram per milliliter. So salt water should be just a little bit higher than that because of the weight of the salt in the water. But here we go for that one. All right, this one here, we have a temperature conversion that we have to work through. And I do want to point out that we don't want to go directly to Kelvin. I recommend that you go to Celsius first, and then you go to Kelvin. So when I grade this, I'm going to look for the Celsius value as well. All right, so we had a few different forms of this equation, and we're going from degree F to degree C. So do I use the form that has the 5 on the top or the 9 on the top? The 5. And the way you can remember that is Celsius is typically a smaller unit than Fahrenheit, so you put the smaller number on top. So 5 over 9. And then we have to subtract the offset first. It should be 95. And then we minus 32. All right, so when doing this, be careful of your order of operations. I'm just going to go ahead and do it stepwise so it's really clear about what's happening. All right, so we have our just to be clear here, first I went ahead and applied the addition rule, knowing that this has an infinite number of decimal places. So whatever this one had, we have here, which was 2. And then here we're following the multiplication rule, giving us 4 significant figures, so we get 4 here. All right, so at this point we have 4 sig figs. And then to go to Kelvin, you just take your value in degree C, and am I going to add or subtract the 273.15? We're going to add it, yes. So plus 273.15. So based off the addition rule, we have 2 decimal places there. Here we have infinite, that's the definition. So we're going to get 2 in our final answer. We're actually going to gain a sig fig here. Here was a heat capacity question. So the equation was Q is equal to MC delta T. Alright, so taking a look at the question here, the question is asking us how much heat or how much Q. We're given M here, and to raise its temperature by 25 degrees C. So the question now is that TF or is that delta T? That's delta T, yes. We don't need to actually know what the initial temperature was because we're told the range. All right, I do believe we just plug into the equation now. And just punch all this in. All right, our next question here, how much heat is this in calories? So we go ahead and take our 3 point, and I actually want to do this without clearing my calculator. So 39225. Let's go ahead and keep track of sig figs. I should only have 2. And the units is joules. All right, and then I need a factor to convert from joules to calorie. And what is that factor? It's your heat capacity of water, right? 9.4 times 10 to the 3 calories. And just like the previous example, I could say that this is 9.4 kilocalorie. How else could I say kilocalorie? I just put a capital C, right? So you could say 9.4 and then calorie with a capital C. Recall that the capital and lowercase mean something different. If it's capital C, that implies a kilocalorie, and we oftentimes call that a food calorie. All right, so here we had to identify endo and exothermic, as well as chemical and physical change. We don't need a calculator here, but remember that when we use the word exo and endothermic, we talk about a system. So let's call this box here our system, and that'll be whatever we're talking about in the problem. And if heat is going out, what do we call that? Exothermic. And if heat is going in, we call that endothermic. And heat's going in that case. All right. So you can also think about these in terms of whether temperature is going up or down. If temperature is going up, that means that you're putting heat into it. If temperature is going down, heat's coming out. All right, so for melting ice cubes, which one is that, exo or endo? Endothermic. And I will just abbreviate these as endo or exo. All right, condensation of water vapor, that's exo. Baking a cake, endo. Frying an egg, endo. And then burning propane, exo. So you can think of these two things being related, cooking at home. So one, you're going to be burning some fuel to give off heat to go into whatever food you're cooking. All right. Take a look at the next part here. So chemical or physical change. Chemical change is defined as the composition is changing or a chemical reaction. A physical change, your composition is staying the same. And most often there are things like phase changes or you're breaking something, things of that nature. All right, so A, digesting food, and I'm specifically talking about after it's in your stomach. Would that be a chemical or a physical change? It's chemical, yes. And I just wanted to be clear here because you could argue that while the food's actually in your mouth, it's technically both because you're breaking your food down with your teeth. That's a physical change. And then enzymes actually start working in your mouth right away. So it's both chemical and physical in your mouth. But by the time it gets to your stomach, it's all physical or chemical at that point. Next one here, breaking glass. Physical. Baking bread. That is a chemical change. The way you can remember that, something like that, is that whenever you cook something, you are changing the chemical structure of it. And when you can think about it, when you're baking your bread here, after it's baked, you probably can't get your eggs and your flour back, can you? It's pretty much done, Dill. You're not getting your eggs back. All right, next one here, mixing sugar and water. That is a physical change. Neither one of them will react. And then the last thing here is melting aluminum metal. It's a physical change, yes. All right.